suppose now that we have a collision. Before collision, we have an unknown mass moving at an unknown velocity, but in what we're going to call the x direction, toward a known mass at rest. Okay, so we know m2, we know the velocity of this thing before collision, it's 0. We don't know the speed or the mass of this object, but we do know it's moving in the x direction. After collision, we know everything about the motion. We know the velocity, or the speed, and the direction of motion, which is v1 and theta 1 in this case. v1 prime, that is, and theta 1, v2 prime and theta 2. I should probably put theta 1 prime and theta 2 prime to indicate that those were after collision. But since there were no non-zero angles involved before collision, it just didn't occur to me, but that would have been a good idea. Okay, so what do we know at this point? Well, we know that whatever m1 and v1 are, the total momentum before collision is m1 v1, and it's in the x direction. We know that we can find the velocity components in the x and y direction for each of these masses, and as a result we can find the momentum components for each mass in the x and y directions, and as a result write down expressions at least. Well, since we know all these things, we can actually write down the actual quantity, the actual total momentum in the x direction and in the y direction after collision. I'll note that these arrows aren't really all proportional to what they ought to be. There's a little bit of problem here with conservation of energy. This arrow is longer than this one, which means that the mass m1 has more kinetic energy after collision than it did before, and that can't happen unless somehow m2 imparts some kinetic energy to it, but m2 was sitting still, didn't have any kinetic energy to impart. So the arrows here aren't really accurate. This is just a more or less a schematic. It wasn't any attempt to do an accurate depiction of these velocities. Okay, before collision, as we said, we have p1x, the momentum of the first object in the x direction is just m1 v1. And everything else is 0. The second object isn't moving, so it has no x or y momentum. And the first object has no velocity in the y direction, so it has no y momentum. After collision, we have velocity v1. We have mass m1 moving at velocity v1 at angle theta 1. Its x velocity will therefore be its mass times the x component of v1 prime. And the x component of v1 prime is v1 prime cosine theta 1. Similarly, the first object has a momentum in the y direction that's equal to its mass times its y velocity. The y velocity is v1 prime times the sine of theta 1. So we have this for the y velocity. And we have similar expressions for the second mass. In each case, taking the mass times the x component of the velocity to get its the x component of the momentum, and times the y component of the velocity to get the y component of the momentum. And I will note that I should have a prime down here on my P2. If we then write down what we know, our total x momentum before equals our total x momentum after collision. If we write down the total x momentum before here, it's just m1 v1. After, it's the m1 v1 prime cosine theta 1 and the m2 v2 prime cosine theta 2. We note that v1 prime, v2 prime, m2, theta 1 and theta 2 are all considered to be known. The only unknown we have in this equation is m1. Now, same thing with the y momentum, total before equals total after. There's 0 y momentum before. Neither mass has any momentum in the y direction before collision. After collision we have m1 v1 prime sine theta 1, m2 v2 prime sine theta 2. And these are our y momenta after collision. This is an equation where again the only unknown is m1 here. v1 prime theta 1, theta 2, v2 prime and m2 are all known, so we can solve for m1 here. We can substitute back in here for m1, and then we can solve for the unknown v1. Now I think I said a minute ago that m1 was our only unknown, and that wasn't correct. We have both m1 and v1 unknown here. So down here m1 is the only unknown. We solve here for m1, put it up here, and then we can solve for v1, and we can get the unknown mass and initial velocity of the first particle, or the first ball, or whatever it happens to be. Note that any time we know everything except for two variables, we can solve these momentum equations, the x and y momentum equations, provided we have some momentum in the y direction, of course. The variables don't have to be the initial velocity of the first ball and the mass of the first ball. They could be just about anything. So this analysis can be generalized in a lot of ways.